Hi everybody, and welcome to example 5 on page 65. This discussion is going to kind of wrap up the section for us here. Okay, so let's take a minute to read this. So let V and W be finite dimensional vector spaces of equal dimension n. Let beta and gamma be bases for V and W. Okay, and let A be the matrix of T, taking beta coordinates to gamma coordinates. So this is the same idea of a matrix of a transformation that we talked about earlier in this chapter. We'll make one last assumption, and that is that T from V to W is invertible. Okay, now I want to focus our attention on the diagram that we're given over here to the right. This is the same diagram that we drew a lot when we were talking about section 2.2 and 2.3. Okay, so let's kind of unpack it and remind ourselves of what the pieces are here. Okay, so there's an LA sitting in our diagram, and remember that notation represents left multiplication by A, okay, which happens to be the matrix of our transformation. So I'm going to just remind you of that. So this is the left multiplication by A transformation. Okay, now, if you look carefully at the diagram, there are two things that are sort of new, okay, that didn't appear in this diagram when we drew it earlier in the chapter, and those are these two pieces, phi beta and phi gamma. Okay, those are the standard representation maps that we just talked about. Okay, and remember, they just take vectors and map them to coordinate vectors. Okay, so even though we didn't use that terminology when we drew this diagram earlier, those mappings were already always there. Okay, just we have a name for those now. Okay, and so just kind of stepping back from this for a minute and thinking big picture, what information this diagram is telling us. Okay, we've got the high road up here that tells us that T is a linear transformation that takes vectors in V and spits out vectors in W. And then down here on the low road, there's a corresponding calculation that takes coordinate vectors of things in our domain, left multiplies by the matrix of the linear transformation, and then comes up with a coordinate vector representing our output. Okay, same interpretation that we gave to this diagram earlier. Okay, now what I'd like to put as a part of our diagram now is the additional assumption that we made. Okay, that T is an invertible function, which means that there's a linear transformation T inverse that takes us from W back to V. Okay, and what's interesting is, given that that's true, that means that there has to be a matrix for that inverse transformation. In other words, there's some matrix, we'll call it B, that takes us backwards in this diagram. Okay, and we could ask the question, what is the relationship between the matrices A and B in this diagram? Well, you might suspect that since the relationship between T and T inverse is one in which if we take T and compose it with T inverse, we get the identity map, maybe there's a similar relationship between the two matrices. Okay, if we take A times B, we get some sort of an identity matrix, and that turns out to be exactly the case. And it leads us very naturally to this definition. Okay. So let's start with an n by n matrix, kind of like the one that we had up in the example before. Then A is invertible if there exists an n by n matrix B such that AB equals BA equals the identity matrix. And I'll put an n on it just to emphasize that that identity matrix is n by n. And we denote the inverse of the matrix by A inverse. Okay, and it turns out that the matrix B in the picture that we drew up here is exactly the inverse of A according to this definition. Okay, and we'll make a note here. We will talk in much more detail about matrix inverses in chapter 3. Okay. And then there's one theorem that I'll mention just to kind of round out this discussion, okay? And this is a theorem that we'll use a lot, okay, once we get into chapter 3. We're just going to state it here, okay? So let's read it together. Let V and W be finite dimensional vector spaces with ordered bases beta and gamma respectively, okay? And let t going from v to w be linear, okay, and here's what the theorem says. Then t is invertible if and only if the matrix of t, taking beta to gamma coordinates, is invertible. Okay, so we can tell whether a linear transformation is invertible by just looking at the matrix of the transformation and ask if it's invertible according to this definition above. Okay, moreover, we can say one more thing. To get the matrix of the inverse transformation T inverse going from gamma to beta, we can just take the inverse of the matrix T. Okay, so T going from beta to gamma, if we take the inverse of that matrix, that's going to tell us what the matrix of the inverse of T is.